Have you ever wondered why things fall to the ground? Why the planets in our solar system orbit the sun? Or why the moon doesn't simply fly off into space? The answer to these questions lies in a fundamental principle that governs the universe. A principle proposed by Sir Isaac Newton in 1687, the Law of Gravitation. This law has been the cornerstone of our understanding of the cosmos, explaining the motion of planets, moons, and other celestial bodies. It has allowed us to understand why objects attract each other and how this force of attraction influences the motion of objects in the universe. From the apple falling from the tree to the complex dance of galaxies, Newton's law of gravitation holds the answers. Now, prepare to dive into the fascinating world of gravity. So, what exactly does Newton's law of gravitation state? Well, imagine a universe where every speck of matter, from the tiniest grain of dust to the most massive star, is engaged in a grand cosmic dance. Each particle, regardless of size, tugs at every other particle in existence. This is essentially the heart of Newton's law of gravitation. It tells us that every bit of matter in the universe attracts every other bit with a force that is directly proportional to the product of their masses. This means if you double the mass of one object, the force of attraction between it and another object doubles as well. But that's not all. This force is also inversely proportional to the square of the distance between their centers. This inverse square law holds that if the distance between two objects is doubled, the gravitational force between them becomes a quarter of what it was. To put it in simpler terms, the closer objects are to each other, the stronger the gravitational pull between them. But as they move farther apart, this pull decreases rapidly. This principle explains why we don't feel the gravitational pull of distant stars and galaxies, yet we're firmly rooted to the ground by Earth's gravity. Let's delve into some key points of Newton's law. First up is the inverse square relationship. This concept is a crucial part of Newton's law of gravitation. It essentially states that the force of attraction between two objects decreases as the square of the distance between them increases. This is why distant planets experience weaker gravitational forces than those closer to the Sun. More importantly, the inverse square relationship implies that gravity extends infinitely throughout the universe, reaching every corner of space, no matter how remote. Next on our list is the explanation of planetary orbits. Newton's law of gravitation provides a mathematical justification for the elliptical orbits of planets around the Sun. This was a significant advancement in our understanding of the cosmos. Johannes Kepler had previously proposed laws of planetary motion based on observational data, but it was Newton's law that provided the underlying mathematical framework. Last, but certainly not least, we have the Cavendish experiment. In 1798, a scientist named Henry Cavendish conducted the first laboratory test of Newton's law using a device known as a torsion balance. This experiment was vital because it confirmed the accuracy of Newton's law and provided a precise value for the gravitational constant, a key parameter in the law's mathematical formulation. These points highlight just how revolutionary Newton's law was. The inverse square relationship, the explanation of planetary orbits, and the validation through Cavendish's experiment, all of these aspects contributed to a new understanding of the universe. They showed that the same rules governing an apple falling from a tree also govern the motion of celestial bodies. And that's quite a remarkable realization, don't you think? No scientific law is perfect, and Newton's law is no exception. Even the mighty law of gravitation, which has guided us through the cosmos for over 3 centuries, has its fair share of limitations and flaws. Firstly, Newton's law makes a significant assumption. It treats celestial bodies as if they were point masses, meaning it assumes they have no size or volume. This simplification works well for most practical calculations, but it's not entirely accurate. With larger, more irregularly shaped bodies, we need to make corrections. Just imagine trying to apply Newton's law to an object like a planet or a star, which isn't a perfect sphere and has a significant volume. The law needs some tweaking to accommodate these realities. Secondly, the law of gravitation tells us how gravity works, but it remains silent on why gravity exists in the first place. Why does mass attract mass? Newton's law doesn't provide an answer. It wasn't until Albert Einstein came along with his theory of general relativity that we got a more comprehensive explanation. According to Einstein, mass warps the fabric of space-time, creating what we perceive as gravity. It's like a bowling ball sitting on a trampoline, causing everything around it to roll towards it. Lastly, Newton's law starts to falter under extreme conditions. When dealing with incredibly high speeds or strong gravitational fields like those near black holes, Newton's law no longer holds up. Here, the relativistic effects predicted by Einstein's theory of general relativity become significant and provide a more accurate description of gravitational phenomena. So, while Newton's law of gravitation is a foundational pillar of classical physics, it's not without its shortcomings. But remember, these limitations don't negate the law's immense value. After all, it's been guiding spacecraft to distant planets and helping us understand the motion of celestial bodies for centuries. Despite these limitations, Newton's law has stood the test of time. Newton's law of gravitation has left a lasting legacy. This seemingly simple equation, penned over 3 centuries ago, reshaped our understanding of the cosmos, ushering in a new era of scientific discovery. It provided a unified framework to explain the motion of the celestial bodies, something that had baffled scientists and philosophers for millennia. Under Newton's law, the fall of an apple and the orbit of the moon were no longer distinct phenomena, but two manifestations of the same fundamental force, gravity. This idea that the same physical laws govern both the heavens and the earth was revolutionary. It broke down the barriers between terrestrial and celestial physics, paving the way for the development of classical mechanics. Moreover, Newton's law has proven to be a practical tool for everyday calculations. It's used by astronomers to chart the course of planets and comets, by engineers to design satellites and spacecraft, and even by GPS systems to provide accurate location data. Its simplicity and practicality have ensured its enduring relevance in a wide range of fields. But perhaps the most significant impact of Newton's law was on the trajectory of scientific thought itself. It set a precedent for the use of mathematics to describe natural phenomena, a principle that underpins modern physics. It also laid the groundwork for the development of Einstein's theory of general relativity, which refined and expanded upon Newton's ideas. Yet, despite its limitations, Newton's law of gravitation has not been relegated to the annals of history. It continues to hold its place as a vital part of the scientific canon. Its enduring legacy is a testament to the genius of Sir Isaac Newton, whose insights have shaped our understanding of the universe. In the grand scheme of things, Newton's law of gravitation remains a cornerstone of classical mechanics,